All right, hello everyone. We got a good bit to cover for this series of lectures, but this will be the last of our lectures for this course. So once you get yourself through these lectures, that's all the new material that we're going to be learning. We're actually going to be doing chapters 12 and 13. Chapter 13 is smaller and it actually ties into chapter 12 well. So I'm going to cover chapter 13 first, and then uh, go on to chapter 12. Chapter 13 is about equilibrium in reactions. It applies to all chemical reactions. And then in chapter 12, we'll talk specifically about acid-base reactions. Okay, so getting into equilibrium here. Um, in theory, all chemical reactions are reversible processes. Um, you have in this case carbon monoxide combining with chlorine to give us our product here. But at the same time, right, so you have these combining to form our product. At the same time, you have the product that's kind of falling apart back again into the reactants, right? So you always have reactions going in both directions, both the reactants combining to form products, but also the products going the other way, and in this case, breaking up to form the reactants. Okay, so all reactions are reversible processes. It turns out that some reactions really heavily favor one side or the other, but nonetheless, in theory, reactions are always reversible. Okay, so that's what we're going to be talking about today. Okay, this idea of this reversible process. At some point, the system will come to equilibrium, right? So there's forward reaction happening, but there's also backwards reaction happening. At some point, you'll reach an equilibrium where the amount of each component does not change, right? So you reach some equilibrium where the rate at which the product or the reactants are forming product is the same as the rate in which the product's falling apart into the reactants. So there's a balance and there's not a change in the concentration of any of those species. Okay, so if we look here, for example, here's a reactions where we have dinitrogen tetraoxide breaking apart into 2 moles of nitrogen dioxide. Okay, so what this graph is saying is if we look, let's actually color code this here. We're going to make this one the pink line. Okay, and so then that makes the nitrogen dioxide the red line. All right, so at the start, so on the x-axis is time here, right? So at the start of our clock here, we have all of the components are that dinitrogen tetraoxide, and there's 0% nitrogen dioxide in there, right? But then this chemical reaction starts to happen where that reactant falls apart into these products. So the concentration starts to decrease for the dinitrogen tetraoxide and starts to increase for the nitrogen dioxide. All right, so that's as reactant is breaking apart into the products. But you also will have the products going the other direction as well, right? And at some point, the rate of these two will reach a plateaued value. So now at this point here, once it plateaus, the system is in what we call equilibrium. So you can see that now as time increases, the amount of nitrogen dioxide doesn't change and the amount of dinitrogen tetraoxide does not change. Okay. Nonetheless, if you were to sort of zoom in, you would see that although the concentrations aren't changing, that doesn't mean that there's no reaction happening. It just means the rate of the forward reaction is the same as the rate of the reverse reaction, right? So at this point here, we're already in equilibrium. So for these 3 steps here, we're already in equilibrium at this point, right? So the number of nitrogen dioxide molecules is the same for each one of these samples. And the nitrogen and the amount of dinitrogen tetraoxide is also the same in each one of these samples. But nonetheless, you still have reaction occurring, right? So for example, these 2 right here combined to form this, but at the same time, you had this breaking up into these 2 components here, right? So it's not that there's no reaction happening. It's just that the products are falling apart, or I guess in this case, the reactants are falling apart at the same rate in which those products are joining together to form more reactant, right? So the forward and the reverse process are occurring at the same rate. This is, again, what we call equilibrium. And we can see that it's equilibrium because the concentrations of each species does not change over time. All right, so we can quantitatively talk about the equilibrium of a reaction using the equilibrium constant, okay? And this will relate the concentration of the reactants to the concentration of the products. And in particular, one thing I want you to have memorized in your head is K is equal to products over reactants. Okay, products over reactants, products over reactants. You want to have that burned into your brain. Okay, and again, this is going to be a constant. K is an equilibrium constant. So each reaction is different. Each reaction will have a different equilibrium constant. But again, this will relate the concentration of the reactants and the products at equilibrium. So in our example reaction here, it's going to relate the concentration, again, products over reactants. So the concentration of our product over the concentration of our reactant. Okay, so the one came from the one side of my chemical equation, right? That's my product. And the other comes from the other side of my chemical equation. That's the reactant. Okay, so concentration of products divided by concentration of reactants. That's how you set up your equilibrium constant. And then the other thing that we have to do is, because of the mole ratio in this reaction here, where I have 2 moles of nitrogen dioxide being formed from 1 mole of dinitrogen tetraoxide, this too is going to find itself in our equilibrium constant, because we're going to raise the concentration of nitrogen dioxide to the power of 2. So whatever that coefficient is out front in your balanced chemical equation will become an exponent in your expression for the equilibrium constant. Okay, so let's practice a few with regard to these reactions here. So again, what do you have in your brain? Products over reactants. So K, we're going to take the concentration of the products divided by the concentration of the reactants. And this is our first reaction where we have 2 things on the reactant side. So notice that you're going to take those 2 concentrations and you're going to multiply them. That's what this expression on the bottom becomes. Right, so again, products over reactants. Let me move this over, because then the last thing we have to do is account for these coefficients. I don't have anything out front of the nitrogen, so that's just going to stay there. I have a 3 out front of my hydrogen, so this becomes cubed over here in this expression. And I have a 2 out front of my ammonia, so that's going to be raised to the power of 2. Okay, so this is the expression for the equilibrium constant of this reaction. Go to the bottom here. Again, products over reactants. So my product is this silver ammonia ion divided by reactants. Silver. And I have concentration of ammonia. And then I have to add those stoichiometric coefficients as exponents. So there's nothing for the silver and there's nothing for that silver ammonia ion, but I do have a 2 out front for the ammonia here on the reactant side. So that needs to be raised to the power of 2. Okay, lastly, again, products over reactants. So CdBr4, whoops, I'll be good and put the charge in there, 2 minus, divided by the concentration of cadmium ions, the concentration of bromide ions, and then again, going back and adding those stoichiometric coefficients. I don't have anything out front of these, but I have to raise the bromide concentration to the power of 4. Okay, so given a balanced chemical equation, you can form the expression for the equilibrium constant. All right, so now let's use the equilibrium constant can be used to quantitatively talk about a reaction at equilibrium. Okay, so for this experiment here, we have carbonyl chloride, CoCl2, which is a phosgene, a highly poisonous gas that was used on the battlefield of World War I before we had chemical warfare rules. Um, it's produced by reacting carbon monoxide with chlorine gas. Okay, so in an experiment conducted at 74 degrees Celsius, the equilibrium concentrations of the species of reactions were as follows. So it gives us the concentration of carbon monoxide, the concentration of chlorine gas, and the concentration of carbonyl chloride. And we want to write the expression for the equilibrium constant and then determine its value at 74 degrees. I'll note that the temperature, it tells you the temperature is 74 degrees. That's not actually going to factor in anywhere to our math. What's important about that is that equilibrium constants change for different temperatures. So a reaction carried out at 74 degrees Celsius would have a different equilibrium constant than a reaction carried out at, say, 25 degrees Celsius. So when we're talking about our equilibrium constants, you always have to keep a temperature in mind. The temperature has to be the same throughout the problem, basically, and it always will be. But that's why the temperature is given, is because this equilibrium constant is going to be unique to a given temperature. Okay, so I'm actually going to do this. Let's give ourselves a little bit more room. So we're going to first set up the expression using our balanced chemical equation here. K equals the product, the carbonyl chloride, over reactants, carbon monoxide and chlorine gas. Okay, so then we can just punch in those numbers. The concentration for the carbonyl chloride is 0.14. Truthfully, equilibrium constants do have units, but it's different for each it can be different for each reaction. So we're going to kind of gloss over it in this course and not really pay attention to the units for equilibrium constant. So you're always just going to assume that your concentrations are in molarity, and you're not going to worry about units when it comes to figuring out K. Okay. So then the concentration of the carbon monoxide, that would be, now multiply that by the concentration of chlorine gas. Okay, and then I'm just going to punch these into my calculator. Let me actually move it over so I got some room. And I get 216.049. Should be enough. Again, I'm not going to really worry about units. I will say you should attempt this calculation on your own just to make sure that you're punching it into your calculator correctly. In particular, you're going to have to put parentheses around this at the bottom here. Otherwise, you won't be dividing it correctly. Okay, so make sure that you know how to do this. Follow along and punch it into your calculator. Make sure you're getting that correct answer. We do have to worry about sig figs. I have 2 sig figs up here, 2 in this number and 2 in this number. So that means that I'm going to have to round to 2 sig figs. So the equilibrium constant for this reaction would be 220, considering my sig figs. Okay. Now, how do we use an equilibrium constant? Well, so now we have a different set of circumstances. So this is, we'll say it's again at 74 degrees Celsius. And at equilibrium, the concentration of carbon monoxide is 0.2 and the concentration of chlorine gas is 0.1. What is the concentration of the carbonyl chloride? Right, so again, I'm going to use this. This is a different reaction, right? So I don't always have to start out with the same amount of reactant. I can start out, in the example above, they gave the concentration of chlorine gas at equilibrium was 0.054. Well, if I use more chlorine gas, then it's going to change that value. What doesn't change is this ratio here, this equilibrium constant. right? So if I know the concentration, so just like all of our problems, right? If I know 3 of these variables, then I can use it to solve for the 4th one here, for my missing variable. And so that's exactly what we're going to do here. We're going to use the value of K that we just calculated. Okay, so um, and like we do, we're going to use the unrounded value, not the one that we rounded to the correct number of sig figs. We're going to use the unrounded value so we don't incur any rounding errors. And then just pay attention to sig figs at the end. What I'm going to be solving for, my missing variable, is this here, right? So make sure that you can rearrange this equation to solve for your missing variable. You're going to have to multiply both sides by the concentration of carbon monoxide and the concentration of chlorine gas. So this will transform into K times concentration of carbon monoxide times the concentration of chlorine gas equals the concentration of that carbonyl chloride. And that's our missing variable. So then I'm just going to plug in my numbers. So 200, again, I'm going to use that unrounded value, 216,049, so that I don't incur any rounding errors, times the concentration of carbon monoxide, which was 0.20, times the concentration of chlorine gas, 0.1, whoops, 10, and punch that into my calculator. And what I'm going to find is that the concentration of carbonyl chloride in this case would be 4.3209. 8. And again, we're going to say that our concentrations are always in molarity. So that's 4.32098 molar. That's the concentration of carbonyl chloride. Move this up so I have a little bit more room. And then I'm going to have to round to the correct number of sig figs. I have 2 in all 3 of these here, so I'm going to round to 2 sig figs. So my final answer for the concentration of carbonyl chloride would be 4.3 molar in this particular reaction at equilibrium, right? So that's how we use our equilibrium constant. If we're given the concentration of reactants, for example, that was in this case, and we have an equilibrium constant, we can figure out the concentration of the products. Okay. So what we'll see if if you sort of play with this idea again, K is the concentration of products divided by the concentration of reactants, right? So if K is very large, then the reaction will favor the products, right? If K is a really big number, like let's say K is 10 to the 10 or something like that, that means my concentration of products is 10 to the 10 more than my concentration of reactants, right? That's what that ratio is telling me, is whatever the value of K is, if it's a really big number, that means that I have way more product than reaction. Likewise, if K is a really small number, then this is a reaction that favors the reactant side, right? So if K was, let's say that's 10 to the negative 10, that means that this number here is really big and this number here is really small, right? So the magnitude of K tells you which direction the reaction is favored. If K is a really big number, then that means it favors the products. If K is a really small number, then that reaction favors the reactants, or it doesn't really go to completion very much, to the product side. If it's anywhere between 10 to the 2 and 10 to the negative 2, so this is 100 and 0.01, then it's a reaction that kind of has a considerable amount of both products and reactants, right? So first of all, let's write K, products over reactants. If K equals 1, then that means you have the same concentration of products as you do reactants, right? 50-50 if K were to equal 1. So if it's between 100 and 0.01, then there's still kind of an appreciable amount of both products and reactants, at least 1% reactants in the case of K equals 100. So this is a range where we really kind of consider them to the concentration of products and reactants to be important. If K were a really, really big number, so for example, 10 to the 10, we would say that there's pretty much no reactant left over. right? But in this range here, this indicates that neither side is really strongly favored. All right, and the last thing we're going to talk about with regard to equilibrium constants is this idea of Le Chatelier's principle. Okay, Le Chatelier is like a French name, and this is a way that we can kind of tune the conditions of our reaction to drive it in one way or the other. Okay, so this is at equilibrium. We're going to, let's say that we wanted more product. This would be a way that we can sort of tune our reaction conditions to get that goal. So what do I mean by that? So, and you can convince yourself of this using the expression as well, but let's just take a look at an example here. Um, we have nitrogen gas plus hydrogen gas gives us ammonia. That's our reaction. So let's say that we've mixed nitrogen gas, hydrogen gas, and ammonia, and it's come to equilibrium. So I guess, let me real quick. The blue is the nitrogen gas. The red, or I'm sorry, the green is the hydrogen gas, and the red is our ammonia product. Right, so in this particular reaction, I have combined my hydrogen and my nitrogen, and it's reached equilibrium, so my concentration of each of these three species doesn't change. But what if I wanted more ammonia, right? So this is, again, the concentrations on the y-axis. It's not changing over time. But now I want more ammonia. How could I change my reaction conditions to drive this reaction in favor of more product? Well, what I could do is add in a ton of nitrogen. All of a sudden, I increase, nitrogen's blue, I increase the concentration of nitrogen. And what that's going to do, so now I've increased the concentration of nitrogen. What that's going to do is drive this reaction more towards the product side. So all of a sudden, by increasing the concentration of nitrogen, I have driven the reaction more towards the product side. Okay, and you can convince yourself of that using this equation here. Again, K is products over reactants, and K has to remain constant. So if all of a sudden I increase this number here gets bigger, this has to get bigger as well in order to compensate, in order to keep that ratio constant. So this is Le Chatelier's principle, the ability to drive a reaction in one way or another by adding or removing substance. So let's, again, here, what happens if I add any of this reactant, what I'm going to do is drive this reaction in favor of the products, right? Because again, K equals products over reactants. K is a constant, so if this number gets bigger, this number also has to get bigger to compensate. Okay. Likewise, another thing that I can do, another strategy would be to remove the ammonia as it's being formed, right? So if as that ammonia is being formed, I take it out of my reaction vessel, then this number is getting smaller. And so this number has to be smaller to compensate. It will end up generating more product if I continuously remove the product as it's being formed. So both of these ways, adding more reactant or removing product, drives things towards the product side of the reaction. Okay. If I added more product in there, right? So I didn't want my reaction to go, I don't know, whatever, I don't know circumstances, I can't really think of why this would necessarily be desirable, but let's say you don't want this reaction to occur quite as much. Then I could do so by adding more product, right? So then again, using my expression here, if I add and this number gets bigger, then what's going to have to happen in order to compensate is this number will get bigger. So this is a way to drive the reaction in the favor of the reactant side, not the product side. And likewise, I can do the same sort of employ a similar strategy in order to drive it towards the reactant side by removing these reactants, right? So by decreasing the concentration of reactants, if this number gets smaller, this number also has to be smaller. Okay, and again, that's because K is a constant. That ratio of products to reactants has to remain the same at equilibrium. So this is this idea of Le Chatelier's principle. You're driving the reaction in favor of either the products or the reactants by tuning your reaction conditions. Okay, so let's take this particular reaction here. And we're going to sort of figure out what happens in these sort of different conditions. Let's say that we have a reaction at equilibrium. Well, what happens if I add more carbon monoxide? If this gets bigger, it's going to drive the reaction in favor of the products. So this will shift in terms of, does it shift it to the left or to the right? In this case, this would shift it towards the right. So towards the in favor of the products. Okay. The next one is the removal of water, right? So if I start removing the water, the system is going to compensate by driving the reaction back to the left-hand side, back in favor of the reactants. So this would drive, this would drive the reaction to the left, the removal of a reactant. What about the removal of a product as it's being formed, right? So I have my product, hydrogen gas. If I start removing that as it's being formed, that will drive the reaction back in favor of the products. So this would also drive the reaction to the right. Okay, and then lastly, what if I started adding a bunch of carbon dioxide? So if I add a bunch more carbon dioxide, the system will have to compensate by shifting the reaction in favor of the reactants or back towards the left. Okay, so this is Le Chatelier's principle.